Good morning to all. So, in this session, we are going to see about the topic Introduction to Component Basics and Microchip Line under the first unit. Okay, before that, we need to know what is a lumped components because we are going to see the component basics of or else a resistor, inductor, and capacitor in this topic. So the lumped components means it includes wires, resistors, capacitors, inductors, and connectors. So which will behave differently at low and high frequency because the current and voltage vary spatially over the component size, which leads to the concept of distributed components. So then next one is at the low frequency, the lumped will be like this. So the impedances R plus J omega L, where in case of high frequency, it is a distributed component. So which means the transmission line itself will act as a distributed one. Okay, so we are going to see what is the RF behavior of passive components, then what is the skin effect, what is the equivalent circuit model in this topic. Okay, so these are all we know where R is the resistor, L is the inductor which possesses an impedance of XL equal to J omega L. Ideal capacitor has an impedance of X equal to 1 by J omega C. Capacitor will behave as a open circuit DC and low frequency, whereas inductor behaves as a short circuit at a DC and low frequencies. This is the RF behavior of wire. A single state wire on a copper trace on the printed circuit board PCB layout has the frequency dependent of RL and L. So the DC resistance of the copper wire can be given by 1 by 5 A square of this conductivity, where L is the length of the cylindrical or a conductor, where A is the radius, and the symbol represents the conductivity. So the internal inductance L of in is due to the internal magnetic field to the wire, so which is equal to A by 2 into skin depth into RDC by W. So skin depth describes the spatial drop off in current density as a function of frequency F1, permeability and conductivity, the sigma. So skin depth is a measure of the exponential decrease of the current density with the depth applies to the most conductor geometries. So finally, we can observe that for a cylindrical wire, so the L of x can be calculated by mu into L by 2 pi into ln of 2L by A minus 1, where mu is the permeability. We know that. Okay, the next one is the RF behavior of resistors. So this can be done by 1 by pi A square into this the conductivity symbol. So this is the RF behavior of conductors. So initially we saw that RF behavior of wires and this is RF behavior of resistors. How the resistor will behave at the low frequency and high frequency. Okay, so there are different types of resistors at the high frequency. First one is a carbon composition resistance, so which is primarily responsible for notoriously poor performance at high frequency. So it consists of densely packed dielectric particles or carbon granules. So that is very small parasitic capacitor will occurs. So this is the combination of parasitic capacitance and these two will represent the lead and this one is the inductance. So the resistors at the high frequency, we are getting a graph like this. This is a frequency versus impedance where this a resonant frequency will occurs at the high frequencies. So this is the equivalent circuit model of the capacitance between the windings. So the resistors inductors connected with the resistor. Then inductance will be having two C1 and C2 is the capacitance. This is the resistors at the high frequency. The equivalent circuit model is we will be having two L with the one R. At the top, we'll be having two capacitance CA and CB. Got. So this is the difference between the resistors at the high frequency for a wire wound resistance and for a metal film resistors. And this is for thin film chip resistors. So the idea is to eliminate or reduce the stray capacitance which is associated with the resistors. And this is good up to 2 gigahertz. And this is the RF behavior of resistors. This is the most common circuit element in low frequency. So the purpose of using resistors is we know it is used to resist the flow of current by producing the voltage drop. So there are different types of resistors, carbon resistors, wire wound resistors, metal film resistors, and the thin film resistors, and each having its own equivalent circuit model. So in the microwave circuits, thin film resistors are frequently used. That is for RF and microwave because of their smaller in size and a good RF performance. So in equivalent circuit representation, the actual R is more complicated due to their finite lead dimensions and parasitic capacitance. So at a high frequency, R appears as the combination of several elements because of the physical wire arrangements. So this is the equivalent circuit representation of the resistors. The equivalent circuit representation of wire wound resistors is more complex. So the inductance L1 of the wire wound resistors acts as a coil and the stay capacitance as the C1 established between the windings. Okay, the next one is this is the interlead capacitance. C2 is generally smaller than the stay capacitance. So the lead capacitance L2 is also considered. So the impedance of the entire circuit can be written as ZR equal to JW LX plus 1 by JW CA plus 1 by R. So it is observed that at the low frequency when impedance is equal to R, when capacitance C increases, then Z of E will decreases. And this is for the RF behavior of capacitors. So in most RF circuits, the chip capacitors will find a widespread application for the tuning of filters and matching networks, as well as in biasing circuits for active components such as transistors. And this is a general formula. C can be written by epsilon into A by D, where A is the circuit plate area, D is the plate separation. So ideally, there is no current flow between the plates. However, at high frequency, the dielectric becomes lossy. So the impedance can be written by 1 by GE. So GE represents conductance of T and J into omega C. So omega represents the acceptance. So in this expression, so the current flow of the DC is due to the conductance with this gamma of DIE. So the conductivity of dielectric is now a customary to introduce the laws of tangents. So which is given as a tangent of del is equal to uh, the symbol of DIE by omega C, which is the sigma of DIE by omega C. So the corresponding the electric equivalent circuit with the parasitic load inductance L. So the series resistance RS describe the losses in the lead connectors and the dielectric loss resistance can be written like this. So which is equal to 1 by the conductance. And this is RF behavior of inductors. The equivalent circuit is L connected in series with RS, which is parallel with the C of S, which is the compensating effect of all distributed CD. And this is the inductor equivalent circuit where the resonant frequency is equal to 1 by 2 pi square root of LC. So this we know for inductance. Xc is equal to 1 by omega c, which is equal to 1 by 2 pi Fc. So here the skin effect is an important to mark question. Then this is the chip inductor, where the surface mounted inductor still come as a wire wound coil. So these are compatible in size to the resistors and capacitors. So the next topic is the microstrip line. So before we saw what is RF behavior at a resistor, inductor and capacitor. So the next one is a microstrip line. So it is a planar type of transmission line that lend itself well to the microwave ICs, miniaturization and photographic fabrication. So this microstrip line is one of the most popular types of planar transmission lines primarily because it can be fabricated by photolithographic processes. And this is the microstrip transmission line. So this A represents the geometry of this, B represents the electric and magnetic field line corresponding to this microstrip line. So this is a type of electrical transmission line which can be fabricated with any technology where a conductor is separated from a ground plane by a dielectric layer known as substrate. So it is used to convey the microwave frequency signal. So this would constitute a simple TIM transmission line with the phase velocity Vp is equal to C and propagation constant equal to K naught. And this is the formula for effective dielectric constant, which is equal to epsilon r plus 1 by 2 plus epsilon r minus 1 by 2 1 by square root of 1 plus 12 d by w. And this is the characteristics impedance is at naught value. Then finally attenuation will be calculated with this equation. Okay. So the attenuation due to the conductor loss finally is given by the alpha of C is equal to Rs by Z naught of W. Okay. And this we know the loss at tangent of the dielectric is given by this at tangent symbol. Okay. So remaining we'll see in next class. Thank you.